So you may or may not have noticed that your tests were graded and entered here the other day. I'm not sure if you guys are still able to see those things or what's going on with that, but I still am waiting on a few students to finish taking their tests. So it'll be, but once, once those people are finished, we'll pass the chapter 2 ones back. And I put the chapter 1 test key on the content library if you needed to look at that. It's there and you're welcome to do that. Okay. Today we're going to talk about the graphs of sine and cosine functions. This is 3.1. And we're going to start with like a little bit of an info dump here. So I'm going to make like a little bit of a table here. So these are going to be the rows in my table. And then we're going to have 2 columns in our table. And I know that maybe not every one of the terms here in this table is going to be familiar, and that's okay. We'll take a moment and define what we mean by each of these things here in a moment. So just like we did in chapter 1, we're going to kind of describe our graphs of sine and cosine as transformations of a parent function. So in the case of sine and cosine, the simplest version of those functions is just like y equals sine x or y equals cosine x. And we've included here several, I think, important attributes for these functions. So for each of them, the domain is all real numbers. That was one of the things that we spent all that time last chapter developing, is we extended the definitions for sine and cosine. So now we can take the sine and cosine of an angle of any size rather than be limited to things between 0 and 90 degrees. And if we remember our unit circle, since the value of sine and cosine is linked to the coordinates on the unit circle, the x and y coordinates, the largest coordinate that we can ever have on the unit circle is a coordinate of 1, where it crosses one of the axes. So 1, 0, or 0, 1, or negative 1, 0, or 0, negative 1. So that's going to give us our bounds for our range. So the lower bound being negative 1 and the upper bound being positive 1. Off to the right, we've included, I've drawn in here the graphs for sine and cosine respectively. So the top one is sine and the bottom one is cosine. Notice that both of these graphs look like waves, right? And not just any old waves, but they look to be like repeating over and over and over again, right? That is, in fact, what is happening. You're seeing the same pattern of graph over and over and over again. That's one of the features of sine and cosine. In a moment when we start actually drawing the graphs by hand, we'll talk about why that's occurring. Also, circling back to chapter 1, we note that the symmetry of sine is odd. It should be easy to see that by looking at the picture, because you notice that, like, this piece, if I reflect it across the x and then across the y-axis, would lie exactly on top of that piece, right? So that was what we described as odd symmetry. And for cosine, if I take this piece and I reflect it across just the y-axis, it would lie exactly on top of that piece. That's what we described as even symmetry. And really it's like the entire piece, right? If I reflect it across the y, all of that overlaps. And if I reflect this across both axes, all of it's going to overlap. But it's easier to see it if you just kind of look at one little chunk of it. And then we have these 4 terms that maybe we are not very familiar with. So the terms amplitude, midline, period, and frequency. And we see that those are the same for both sine and cosine. Let's define what we mean by those 4 terms right now, so it's a little bit more clear what it is that we're talking about. So we say that the amplitude of a wave is 1/2 the distance maybe we should say 1/2 the total height of the wave. That is, it would be half the distance between the maximum and minimum values. So let's draw a little picture with what I mean here. So the total height of this wave is going to be like, oops, if I take like the lowest point and the highest point, the total height would be like this distance. We're looking at just half of that. So like that distance would be the amplitude. Is everybody okay with that idea? And again, the visual is probably the more useful part of this than the in words definition. At least in terms of like practical use. We'll use the in words definition to kind of like develop some ideas, but when it comes time to actually looking at a problem and trying to determine the amplitude, that's going to be more valuable. The picture will be more valuable to us maybe than the words. Okay. Next up is the midline. Okay. So the midline of a wave is the average value of the wave. It's basically that a line that cuts the wave in half, and it should lie halfway between the maximum and minimum y values. So if we combine this idea with the idea of amplitude that we just talked about, these two features are related in that the amplitude is the distance from the midline to a maximum or minimum. So again, let's draw a little picture to kind of illustrate what we mean by the midline. I did it that way. Let's just take this one. Oops. That's going to be way easier. Okay. So that would be like our midline. So when we say divides it in half, what we mean is like we have an equal amount of area between the graph and the midline that is above the midline as would be underneath the midline. And you might say, well, I see 3 pieces above and 2 pieces below, but you have to remember the graph is going on forever in both directions. So there is really an equal amount of area above the midline and as there is below the midline. Is that okay with you guys? Okay. And then to relate this back to the amplitude now, so this distance between the midline and some maximum or minimum is also, we could also define the amplitude that way, since these two quantities are related. Are we okay there? Okay. So the period of the wave is the length of one full cycle of the wave and we say that waves that repeat, or graphs whose waves that repeat, are said to be periodic. So functions like sine and cosine, whose waves repeat, are called periodic functions. And we'll explain here in a moment how I know that, or why we know that they're going to be repeating, or why we observe them repeating. I mean, I've shown you the graph already, but it's maybe not so clear how we're generating the points on this graph. We'll explain to you how I'm generating these in a moment. And the last of these terms is this term frequency. Okay, so we say that the frequency of a wave is the number of cycles a wave completes in 1 unit interval. That's probably not terribly descriptive for us. The big takeaway here, though, is that the period and frequency are reciprocals. So that's the big takeaway there. And I had actually wanted to draw a picture for period, and I just got excited and forgot to put it in there. So let's make a little space with the magic of OneNote. Come here. What is it? That's fine. Okay. Okay. Okay, so the easiest place to kind of see a period is to start at one of these maxima or minima. So for the sake of argument, let's say we start here. And we're going to look for one like non-repeating cycle. So the graph starts off, it goes up and hits a maximum, and then it goes down, and then we're back to our minimum, right? So this is one cycle, what you're seeing in green. And this distance is one period. So this distance should be measured by the x-axis. And again, the part for the period that's going to be most practical to us, the part that's going to be most useful, is the visual part, is being able to kind of identify from looking at a picture what the period might be. Is everybody okay with that idea? Bueno. Okay. So, when we graph things in Chapter 1, or when we graphed a transformation in Chapter 1, we needed some points from the parent function, and then we're going to transform them, right? So the question becomes then, where are these points for sine and cosine coming from? And what would be the key points that I need in order to graph something? Well, the tool that we're going to use to do the graphing is going to be our unit circle. Should have shrunk it that way. Okay. So let's say that we're graphing y equals sine x. Everybody okay with that idea? So in this case, x is some kind of angle measure, and y is the value for sine. Is everybody okay with that idea? So I can get both of those things by looking at the unit circle. So for example, when we are at 0 degrees, the value for sine is 0. And then when we're at 30 degrees, the value for sine is a half. And when we go to 45 degrees, the value for sine is root 2 over 2, which is like 0.707-ish. So I know it's a little bit more than a half. And at 60 degrees, it's the square root 3 over 2, which is like 0.866. And then at 90 degrees, the value is 1. And then I keep on going. So 120, the value is root 3 over 3, or sorry, root 3 over 2. And I just kind of keep going. So that would get us all the way, oops. We'd have worked our way all the way around to one trip around the unit circle, right? Now we're back at 360 and 0. But if I keep going, if I have 390, the value is 1/2 again, right? So I'm just going to keep getting this section that I'm pulling from the unit circle over and over and over again in both directions, right? Because I could just as easily have gone clockwise around the unit circle instead of counterclockwise, right? So my key points are going to be these ones coming from my unit circle. Now, do I really want to use all of these points when generating this graph? Heck no. That's too many points for me to bother to transform. It's too time consuming. It's too tedious. Which are the ones that really matter? Well, I want to make sure that I have the x-intercepts, the maxima, and the minima. So all I really want are these 5 points. So for y equals sine, I want 0, 0, 90, 1, 180, 0, 270, -1, and then 360, 0. Or if we're graphing in radians, which is probably the more common thing that we'll be doing. Why do you suppose it's more common to do our graphing in radians than degrees? The numbers are smaller, right? 2 pi is 6.2 and change versus 360. If you're graphing something on a sheet of paper, it's a little bit less work to put on 6 tick marks than to, try to scale something out to 360. You know what I mean, guys? Elizabeth, of course. What would change if we were instead using cosine? Well, instead of plotting the angle with the y-coordinate from the unit circle, we'd be plotting the angle with the x-coordinate from the unit circle. So for example, we'd be starting at 0, 1, and then 30 root 3 over 2, and then 45 root 2 over 2, etc. Oops. Be like right there. So cosine is going to look like this. But again, we don't want all those stinking points. All we want are the kind of corresponding points for 0, 90, 180, 270, and 360, the ones where the graph is either crossing the x-axis or at a maximum or minimum. Or if we're doing this in radians, So these ones are the key points. So whenever we're graphing a sine or cosine function by hand, these are the points that we're going to be using to do our transformation. So if you guys remember back to chapter 1, for some parent function that we defined as y equals f of x, any transformation can be written as g of x equals a times f of 1 over b x minus h plus k. And we can find the transform points then by using the transformation map bx plus h, ay plus k. So those are the tools that I'm going to use to actually graph. So the idea, I'm going to use my key points. I'm going to determine the values for a, h, and k, or I'm sorry, a, b, h, and k, based on that general form. And then I'm going to perform my transformation using that map and then graph my new points. Is everybody okay with that plan? Let's do an example here to help kind of cement that. Oops. Okay. So let's say we want to graph y equals -3 sine of 1/2 x minus 3 over pi, or I'm sorry, minus 3 pi minus 2. So the first thing that I'm going to want to do is try to rewrite my function so that it's in this form. In this case, what does that really mean that I need to do? Well, notice here that the 1/2 b is not the coefficient on the x. The coefficient on the x is 1. Did you guys see that over here? So I need to do the same thing down here. So I'm going to factor 1/2 from both the 1/2 x and the minus 3 pi. When I factor the 1/2 off of 1/2 x, it just becomes 1/2. I'm sorry, it just becomes x. What do I get when I factor 1/2 out of 3 pi? Yes, sir. Not pi over 2. So when we factor something out, it's like we're dividing, right? So what's 3 divided by 1/2? 6. So I should have 6 pi here. Are we okay with that idea? So that's a common place that we make mistakes, is we forget to factor the 1 over b out. So now I can see that my a value is -3, my b value is 2, my h is pi over 6, and my k is -2. Is everybody okay with that idea? Very easy to make a mistake on the H there. I think on the Chapter 1 test, I think I caught almost everybody with this same trick on one of the problems there. Now that I have this, I'm going to go ahead and write my transformation map. Is everybody okay with what I've done there? So again, I just used that map and filled in the values for A, B, H, and K. And now I'm going to take my key points for sine. And again, as I mentioned before, more often than not, we're going to be doing this with our coordinates and radians. Oops. I'll take that first one. So now I'm just going to plug them in. So when I plug 0 in for x, I get just 6 pi. When I plug 0 in for y, I get -2. When I plug pi over 2 in for x, I get pi, and then plus 6 pi is 7 pi. And then when I plug 1 in for y, I have -3, and then -2 is -5. Everybody so far so good with how I'm doing this? Okay, well, I'm just going to write down the rest of them rather than saying it out loud because it doesn't seem like I really need to do that. Okay. And now I will go ahead and I'll plot my points. So I've made 5 tick marks on the x-axis, or on the y-axis, going down, and 1 tick mark going up, because my y values are from -5 to +1. And then my x values are all in terms of pi here, right? So what do you think I should be going up by in my on my x-axis? Going up by 1 pi, right? And that seemed like that would make the most sense. So let's do that. So 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi, 9 pi, 10 pi. So 1, 2, 3, 4, 5, 6 pi, and -2. And then 7 pi, -5. Then 8 pi, -2. 9 pi, +1. And 10 pi, oops, -2. So there's like my 1 period. What if I'd asked you to extend this to fill the space? So like we have all this empty space to the left of our graph. Let's kind of fill that up. Do I need to generate more points using my transformation map? No, because they're going to be basically the same points that I have already. The only thing that's going to be changing is the x-coordinate, right? But it's easy to see that because at just every tick mark I have something different. So the next tick mark back should be a maximum. And then I'll have another on the midline. And then I'll have another minimum, another on the midline, another maximum, and then another on the midline. So there's my graph with the space filled. It was easy to do that after I had that first period because all I did was continue the same pattern in whatever direction I was trying to extend to. What do you guys think? So far, so good? Okay. Yes, Kristen. Of course. You're welcome. Let's go back to our table there that we drew at the beginning. And I'm gonna add some columns in here, or 2 more columns in. Oh. Maybe I won't. Maybe I'll just copy it, the format. I forgot I put those graphs off to the side. It's going to be tough to, I don't want to move them around because I already drew on them. So let me just do that. And we'll just do it down here. You can add 2 columns if you have the space to do it, though. There's no reason you wouldn't need to do, or couldn't do that. Okay. So we've done this for the parent function, sine and cosine. Let's do this now for their transformations. So if my domain for sine was all real numbers, and I do some transformation to that graph, I shift it left to right or up or down or stretch it some way vertically or horizontally, what is the resulting domain going to still be? Still has to be all real numbers, right? I can't do anything to that graph to make the domain smaller using our transformations. So the domain is going to remain the same. Will the range remain the same if we do a transformation to it? No, that's going to change. So what 2 things can we do to the graph that are going to affect the range? Well, if I shift it left or right, is that going to change the range? No, right? Because shifting it left or right is going to change the x-coordinate, not the y-coordinate. If I stretch or shrink it horizontally, is that going to affect the range? No, right? Again, that's affecting the x. It's a horizontal thing. If I stretch it vertically, is that going to change the range? Yes. How is it going to change the range? Is it going to be multiplicative or additive? Multiplicative. Good. And if I shift it up or down, is that going to affect the range? Yes. Good. Would that be multiplicative or additive? Additive. So the thing we have to be careful about is that the vertical the vertical stretch or shrink could be a negative number. So I'm going to have to be a little bit careful. So the easiest way to deal with that is by just using the absolute value. So we'll have k minus the absolute value of a, and then k plus the absolute value of a. If we do these transformations more often than not, we lose our symmetry. So I'm just going to put a dash through there because it's not necessarily conserved. Continuity, though, is not going to change, right? If the domain is still all real numbers, you know, the graph has to be continuous everywhere still. The amplitude now. The amplitude was 1. That's the distance basically from the midline to a maximum or minimum. It's a distance though, right? So which transformation is going to affect that distance? It's going to be one of the y ones because we're talking about an up and down distance, right? So if I take the whole graph and I just move it, I shift it up or down, is that going to change that distance? No, right? Because all I've done is pick the graph up. It's still the same graph in a new location. So the transformation that would affect that distance is the stretch or shrink. Everybody agree with that? So my amplitude is going to change from 1 to the absolute value of a. The reason we have the absolute value on there is an amplitude is a distance, so it can't be negative. The a coefficient could be negative. That's why the absolute value is there. Everybody okay there? Okay. The midline is the part that divides the graph in half. If I stretch it, do I still have the same amount of the graph above and below the midline? Sure I would, right? So think about it this way, like here's my midline. Here was it before. If I stretch it, that was a bad example, but if we stretch it, it still has the same amount above and below after it's been stretched, right? Now it's a different amount than it was before, but the two amounts are still equal. Do you guys kind of see that? So that's not going to change the midline location, but what would change the midline location? If I shift it up or down, right? If the graph moves up or down, that midline's now got to be at a new location because I've picked up and moved the entire graph. Do you guys agree with that? So the midline now is going to be y equals k. It was y equals 0, but the k is what controls the up and down shift. That's going to be the resulting new midline. The period is a horizontal distance, right? It's a length horizontally. Which coefficient is going to affect that? A, B, H, or K? So I think I heard somebody say H. So H is a shift. So we're just going to pick it up and move it. Did the distance change if we just pick up and move left or right? No, but you're on the right track. What are we going to have to do to make that distance different? Like stretch it or shrink it, right? Which of the coefficients are in charge of the horizontal stretch or shrink? The B. And just like before, it's going to be a multiplicative. So the old period was 2 pi, and the resulting period will be 2 pi times b. And I'm going to put the absolute value around b, again, because b could be negative. But period is a length, so it has to be a positive number, so we'll just take the absolute value of b. And then the frequency was easy because it's just the reciprocal of the period. So if the period was 2 pi times the absolute value of b, the frequency is just 1 over 2 pi times the absolute value of b. So if we go back to the graph that we just drew a moment ago, let's figure out the amplitude, midline, period, and frequency for that graph. Sound good? Everybody's okay with my abbreviations here, I hope. They should be pretty obvious what I'm abbreviating. What is the amplitude going to be for this graph? So remember, the amplitude is the absolute value of A. Our A in this case is -3. So our new amplitude should be 3. So the midline, what's the new midline gonna, or what's the midline gonna be here? Okay, so it was y equals 0, and now it's changed to y equals -2. Or I should say, the midline we know is y equals k. Make sure that you guys are writing the y equals part and not just writing a number. A midline is a line, so it needs to be written as the equation for a line. The period is 2 pi times the absolute value of b. In our case, the absolute value, or the value for b is 2. So our period should be 4 pi, which makes sense, right? If we look at the distance from the start of one period to the end of one period, it's matches, right? The distance between 6 pi and 10 pi is 4 pi. Everybody agree with that? So that's a good little checker that you can do to make sure you've done the transformation right. And the frequency then we know is just 1 over the period. So that's got to be 1 over 4 pi. Oh, excuse me. We should also probably do the domain and range here, right? What's the domain going to be for this graph? Yeah. In fact, for any sine or cosine graph, the domain is all real numbers. That should be easy to remember. The range, we said, was k minus the absolute value of A, comma k plus the absolute value of A. So in our case, the k was -2, and A was -3. So we end up with -5 to -1, which, again, you'll see matches up. Oops, sorry, not -1. It's +1. You'll see matches up with exactly what we're seeing on our graph, right? The minimum value to the maximum value. What do you guys think? I think this is probably a good place to stop. You're bombarded with a lot of information here today. It's before we move on and try to do some other task. I think it would be worthwhile to spend a little bit of time letting you guys soak this part in, because I know that this was probably new for just about all of us. So from the homework, you guys should be able to do 1 through 6 and then 9 through 12 and worksheet 1. So you guys have a good 20 minutes here still left of class. My suggestion to you would be to take that time to get started on one of these. If you have questions on anything, please feel free to come up and bother me. It's no bother at all. But that's it for today. Sound okay?